Hi class, this is Dylan Blair. In this video we are going to be going over 8.2 examples, which is converting Cartesian to polar and polar to Cartesian equations now rather than just points. This is the last video for this week, the week of, March 18th through the 20th. Okay? So let's dive into it. So first, let's go through 3 examples for converting rectangular to polar equations. So the first one, we have 2 ways that we can kind of think about this. Actually, the first 2, there's 2 ways that we can think about it. The first way that we can think about it is we can just plot it out. This is A. We can just plot it out and we can say X, Y. Note that your radius is usually the output. So if you cheat and look ahead to part C, your radius is a function of theta. So theta is your input and radius is your output. Well, no matter for part A, no matter what the radius is, we always have a theta being equal to pi force. So we could say radius being 0 right there. Radius being 1, we're at pi force. Radius being 2, we're at pi force. Radius being 3, we're at pi force. And we end up just lying on this line. Okay, so this is the quick and easy way to do it, because we see that we are just increasing at a nice linear rate, and we're going right one, up one, right one, up one, and so we just get y is equal to x. Okay, it's just a linear line going through the origin. Now, the other way that we can do it is we can actually use some information that we know. So let's change colors on this. We can say that we know tangent of theta is supposed to be equal to y over x, and we know theta is pi force, right? So tangent of pi force is equal to square root of 2 over 2 over square root of 2 over 2, which is equal to 1, and this is still equal to y over x. And we can take this last component, that we know that 1 is equal to y over x now, and multiply x over into both sides. So we have x is equal to y, or y is equal to x. It means the exact same thing. Okay? That's 2 ways that you can conceive or approach doing part A. Part B, similarly, we have an easy way and we have more of a way just kind of using our tools. Okay? So now the difference with this one is that, let's draw out our axes first, is that we are keeping our radius constant. And it doesn't matter what theta is. It doesn't matter what our input is. Our output's always 5. So we could say radius being 5 right here. And theta is 0. Theta is now maybe pi force. Radius is still 5. Theta is pi halves. Radius is still 5. Theta is 3 pi force. Radius is still 5. So on and so forth. Hopefully you guys kind of get the picture on that. Okay, let's connect the dots and complete the circle. So we know that this radius is equal to 5. Okay, so now from this we can kind of use our knowledge from just college algebra. This is just a circle with radius 5, and the equation for a circle that's going through the origin is x squared plus y squared is equal to the radius squared, which would be 25. Okay. Now, what's kind of funny is if we use our tools instead, rather than knowing the equation of a circle, our tools indicate x squared plus y squared is equal to hypotenuse squared, right, for this triangle. Well, that's the same thing. X squared plus y squared is equal to radius squared. And so that ends up being equal to 25 still. and we're done. Whichever way you want to approach it, it's more so the concept of that we approached it differently, but regardless, we got the same answer. Okay, and for the third one, we have r is equal to 4 cosine of theta. Okay, now this one is the tricky one. Okay, whenever you are manipulating these polar equations, you're going to run into some of these tricky ones that you have to kind of think outside of the box and manipulate the equations. Kind of like how we've been talking about how you massage things and you manipulate these equations in order to actually do something to them. Like when we're trying to manipulate an expression, we multiply or massage it by multiplying by something of factor 1, like a 1/2 over 1/2, and it changes how the expression looks, but it didn't really change. Now with equations, how you manipulate an equation is whatever you do to one side of the equation, you do the other side of the equation. Okay, and what we are going to do is, let's just change colors just for the hell of it. We're going to multiply by r to both sides of the equation. Okay. Now you'll see why we did this in 2 seconds once we multiply r onto both sides. So we have r squared is equal to 4r cosine of theta. Okay. Well, the reason why we did this is because of this component right here. So let's talk about this real quick. Well, we know that x is equal to r cosine of theta, and we know y is equal to r sine of theta. So if we only had it just as this guy right here, we don't have that r there, so there's nothing that we can substitute that in for. We can substitute something in for r, but there's nothing that we can substitute in for 4 cosine of theta. So we manipulated it so that we can actually make a substitution. Okay. So now with this knowledge, with knowing x is equal to r cosine of theta, and with this r squared, let's actually change colors on this guy. And by knowing that r squared is equal to x squared plus y squared, we can make some substitutions. So we can say that x squared plus y squared is equal to 4, and we're making this substitution right here, times x. Okay. Now ultimately, we can move everything over. So x squared minus 4x plus y squared is equal to 0 is just a fine equation. Now in this specific example, we could move everything over to the right and solve for y in terms of x, because that's usually what we have. We have x as our input and y as our output. And if we were to do that, we would say that y is equal to plus or minus square root of 4x minus x squared. And that's completely fine too. They're equivalent. This one is more so simplified in a way that we are used to seeing like an equation, whereas this one's doesn't really look like an equation, right? I mean, it still is one because we have the equal sign. That's what defines an equation. But either way, you probably get the point by now. So let's move on. Let's now do polar to rectangular coordinates, okay? So these ones are actually a lot easier. So for part A, we have y is equal to 7. Well, we know that y is equal to r sine of theta. Okay, so that means that 7 is equal to r sine of theta. Now, This means if we want r as a function of theta, so r is our output and theta is our input, we just need to divide by sine of theta onto both sides, and recall that 1 over sine of theta is cosecant of theta, just using a reciprocal identity. So this is 7 times cosecant of theta. So y equaling 7 is equivalent to 7 times cosecant of theta. Okay. Okay, and that's it for part A. Part B, we have x is equal to 3y plus 1. Recall, x is equal to r cosine of theta. Y is equal to r sine of theta. And we just have to plug these in. So we have r cosine of theta is equal to 3r sine of theta plus 1. We can move all of our r terms over. So we have r cosine of theta minus 3r sine of theta is equal to 1. Then we can factor out an r. So we have r times cosine of theta minus 3 sine of theta is equal to 1. And then we can divide across. So the r is completely isolated. It's our output. Our input is theta. And we now have 1 over cosine of theta minus 3 sine of theta. And that would be your answer. Okay. Now part C. We're going to use this exact same idea. X is equal to r cosine of theta and y is equal to r sine of theta. And then we will plug everything in. R cosine of theta plus 2 squared plus r sine of theta squared is equal to 4. Now we're going to need to distribute this guy. Let's actually maybe change the colors a little bit. So we're going to distribute this guy so that when we take r cosine of theta times r cosine of theta, we're going to get r squared cosine squared theta. Then when we take r cosine of theta times 2, we'll get a 2r cosine of theta, and then we'll get another one of those, so that we'll end up with 4r cosine of theta, and then when we take 2 times 2, we get a 4. Then when we distribute through this squared to each term, we get r squared sine squared of theta, and this is all equal to 4. Now, note that r squared, if we were to factor out that r squared and regroup those things around, r squared times cosine squared of theta plus sine squared of theta grouped together, because this ends up being equal to 1, so this entire thing just ends up being equal to r squared. So we can say that this is r squared plus 4r cosine of theta is equal to 4. Okay. Now this is where it gets somewhat tricky, but not as tricky as the other direction of conversion. But either way, we need to completely isolate r to have r as a function of theta. In order to do so, we need to factor out an r. So we'd have r times r plus, I'm missing something. We notice that this 4 right here is what I was missing, and this 4 right there. Those guys cancel out when you subtract the 4 over. So we have equal to 0. Okay. But either way, back to this. Now we have r times r plus 4 cosine of theta, close parenthesis, is equal to 0. Okay. Now what this means is that r has to be equal to 0, or r plus, oh my gosh, r plus 4 cosine of theta has to be equal to 0. Okay, now we give ourselves a reality check. So let's go sneak peek what the original equation was. Well, this original equation is a circle of radius 2, right? That's shifted to the left by 2, okay? And so r being equal to 0 would not capture that. But this could capture it, right? Because r equaling to 0, this guy is going to end up looking like this, just this point, right? Because it never extends out, it just rotates on this point. And so we can get rid of this r is equal to 0, and we can move forward with this one. Now r is completely isolated, so we can say r of theta. So r is a function of theta, r is our output, theta is our input, is equal to negative 4 cosine of theta. And that is our answer. Okay, and that is it for the week on these lecture videos and example videos. If there's anything that you would like to be done differently, don't hesitate to reach out and let me know. I'm more than willing and happy to make adjustments as necessary. So either way, have a good weekend. If I don't see you guys or talk to you guys during office hours, if I do talk to you guys during office hours, whoever's listening, I'll see you then. Bye.